the slide for reinforced. Okay. So that will be a bit more clear. Okay. So before the reparameterization trick, like the reparameterization trick is the solution to the problem of not being able to compute easily the gradients for our variational approximation parameters, because of having the derivative differential operator on the density function. Now, we saw reparameterization trick being one way of solving the problem when we have specific types of probability distributions with continuous variables with specific form. A more general algorithm with its own caveats, however, is the reinforce. So here with the reinforce, again, we have to compute this quantity like before. So the gradient is on the density function. Now what we can do is we can make use of the identity, the derivative. I say algorithm, I meant logarithm. Wait, let me fix that. So that logarithm. So the derivative of the logarithm of a function with respect to the parameters of the function or the input, like in the general case, is 1 over the function times the derivative of the function itself without the logarithm. And then if we can simply rewrite this, right, like we move f here, then the nabla remains on the left hand side. So the derivative of a function with respect to itself is equal to the function times the derivative of the logarithm of the function. So what do we do then? We simply, so also, so that you know, the derivative of the logarithm of a probability density function is often called score function. So score-based models are actually using, also they have something to do with this score function. So the reinforced algorithm or score function estimator, because of this trick, simply takes this identity and puts it into play in the algorithm. So here we'll have the derivative of the density. So that's the derivative of the function here. And then we replace it with the function itself, which is the density, times the derivative of the logarithm of the density. It's a simple rewrite, like based on calculus, like this. The identity, the property for how we can compute the derivative of a logarithm of a function. So now we had an integral that we didn't have a density function in it, so we couldn't really use Monte Carlo estimation. Now with the reinforced trick, we have a new integral that has a density, so we can do Monte Carlo estimation. However, it has one more additional quantity, which is the derivative of the logarithm of the density. And this causes the problem. So you can sample from here, like before. However, on top of whatever variance you will have here, you also have a multiplicative factor, which can like increase your variance of your final estimation, which means that you take a sample, then this sample will be multiplied by a number here, and then the final estimation could be very large, very low, whatever. Like that's variance, right? So on expectation, if you were able to take everything, like the whole integral, all over the place, you wouldn't have a problem. But if you take only 1 or 2 samples, then your values might vary too much. So the gradients are unbiased; they're pointing on average to the correct direction. But if your average depends only on 1 or 2 samples, that's not very stable. Aside from the fact that this here is, we're sampling from any distribution, it's not canonicalized, it can have a very large variance itself. q phi. In the general case, it can, like, let's think of in Gaussian terms, it can have like any value. It can be as wide as possible. No, not as wide as possible, but it can be really wide, which means that the values that will return will be very wide. Okay. However, with reinforce, at least we avoiding the fact that sampling is not differentiable, because we do take samples, but now, so you know, our samples from the density function, of course, are still, you know, constants, but at least now we can rewrite the integral with, you know, in the form of an integral that we can combine with Monte Carlo estimation. Okay. So reinforced journey has very high gradients, a very high variance in the gradients, while reparameterization trick has much lower. However, the reparameterization trick is not general. It works only for specific types of distributions. The variance of the reinforced, of course, is also one reason why reinforcement learning has high variance. Well, that's not the only reason, but one of the two reasons for the high variance in reinforcement learning is that the gradients have high variance. Because in reinforcement learning, usually you cannot differentiate. You've got a simulation environment, but it's a black box. You don't have access to. That's why, you know, reinforcement was actually developed for these settings where you don't have access to the final evaluator. So the values you get are just like given to you. So far, variational inference, as we saw, it was like purely optimization. And per data point, we were optimizing a single or individual variational parameter phi, phi of I, the ith data point. However, that is not very comfortable, because what happens when you want to have a new image, a new input? Then you will have to rerun the optimization algorithm to compute the new optimal parameter. And it's like a loop. Instead, and in the context of neural networks, a more efficient way is to say that we're not going to optimize directly, at least, our variational parameters. Instead, we will have a neural network that is going to approximately tell us what are the near optimal variational parameters. So instead of having the optimal parameters for a variational approximation, the neural network will say, okay, we don't really care about pure optimality. Whatever, our neural network is going to give us some parameters that will be good enough, hopefully close enough. Not quite as the optimal ones, but close enough. So in variational inference, your approximate posterior does not depend on x directly. It's literally a parameter vector that is like, it's a static, it's a matrix in your code that are your Gaussian parameters in the case of Gaussian approximate posteriors. They are not depending x, they're not derived from x. They're not part of a function. Thus, no need for a function approximation. However, for amortized variational inference, we use a function to predict, basically, to regress on what are those optimal parameters. And hopefully, as we train optimally our neural network, these parameters that the network will return will be close to the true optimal variational approximation parameters. So here we still have phi I, but phi I is not the output of an optimization algorithm, of a direct optimization during training. Phi I is the output of a neural network which is itself optimized. So you optimize the network once during training, and then for whatever input you give during training, during testing, this network gives you what are the optimal variational, well, near optimal variational parameters. So, in the case of amortized variational inference for ELBO, we simply replace our standard approximate posterior. Well, it's not posterior, but like the approximate distribution, the variational approximation, with the amortized one, and then we use gradient descent now not on the variational parameters directly, but on the parameters of the neural network. We initialize our neural network generative parameters and the variational parameters. We randomly sample data point, we compute the gradients for our two neural networks, and we'll do gradient descent. We don't have anymore the loop over first of phi, finding first the optimal phi, and then the generative model. So as a pseudocode, this is our inference model, our approximate posterior, that's our generative model. We sample a random mini batch of data. We sample random noise for every data point in our mini batch, so different noise every time, right? We compute the gradients and possibly the ELBO, like the loss, and update using a SGT optimizer, like that's it. And architecture, then this is what it looks like. This is our variational inference, our amortized variational inference. It takes as input a digit, and this neural network, it's a function that will tell you, hopefully by the end of training, what are, let's say, good approximate, good enough, near optimal variational parameters, mu and sigma. And then our generative model, P of x given z, takes these variational parameters, pushes them through its own network, and hopefully generates something that looks as close as possible to zero, like input. If we didn't have the amortized case, we wouldn't really need this. We would just need to optimize like a huge matrix of 1 mu and 1 sigma for all our training points. Here we don't have a matrix anymore, we have a neural network that spits out these values for for whatever input. Is this clear? I think that maybe this is not completely clear. Yes?
Maybe you just said you need to, for the, let's say the not amortized case for understanding, you say that you need to have one big matrix, but that's only would be for one image, right? You would have to optimize again for one image.
No, one big matrix for all images. So you would have like one. So, okay, mu and sigma is basically z. Yeah. Right? It's the same. If you, for the reparameterization trick, we'll call it mu and sigma, but basically in the end, what you really care about is the z. Now, let's say I've got during training, I've got an image x1, x2, x10, right? These are my images. It's going to be a 0, 1, a dog, a bicycle, and whatnot. Now, what I normally want is to make this, to encode this into a latent vector, z. Like that's the whole point of latent variable models, as we've seen. So we want a z1, which takes the form of z11, z12, z1, d, depending the dimensionality you have chosen for your latent space. For your other input image, you will have another latent vector, correct? z2, which is z21, z22, z2d, correct? Now, and if you do it for until the 10th image, you will have another latent vector z10. Correct?
Yeah, and then
Now, when you yes, that's a matrix, right? Like you can, so this, you can organize it in a huge matrix of these row vectors, Z1, Z2, Z10. Now, when you've got variational inference, you care about finding what are the optimal values here. So what are your phi? So this is like a sample from a approximate distribution, right? So Z. Right. So technically it's not Z, it's phi, but okay. So during variational inference, you've got a different phi I for each of them. Like these are, it's a matrix. So what you really care about here is then your matrix phi, which will have phi 1, 1, phi 1, 2, phi 1d. Let's say you need one parameter per dimension. Phi 2, 1, phi 2, 2, phi 2d, phi 10d. So during variational inference, you only care to optimize this matrix, because this matrix will maximize your evidence lower bound for your training inputs. It's a matrix. So what do you do when you've got a new input? You have to recompute the matrix. Correct. What amortized variational inference does is, like, scratch the matrix. Let's approximate the matrix, and it's, you know, generation of the matrix, like row by row, by a function f. We replace the matrix and the need for a matrix with a function f, and in practice a function approximator like a neural network, which receives as input your input x and returns as output your optimal, near optimal parameters phi. They're not going to be optimal. If you want true optimality, you have to optimize direct, right? Like the neural network is a function approximator, it's not a real function. However, the obvious benefit is that once you've trained this and you hope you've trained it well enough, then you can add any input x, and that's it. You're not confined to your data points you've seen during training. You're not confined to a single matrix, like optimizing a single matrix. Is it clear?
Yeah.
So basically this also takes, you can see it from the perspective of an autoencoder, and I think that's also very useful and intuitive. It is important to have both notions of understanding. This is like that's why it's called variational autoencoder. It has an autoencoder structure, it takes one input, it tries to reconstruct it. However, it has some spatial structure in the latent space. In fact, the normal autoencoder does not have a latent space in the first place. Basically, the normal autoencoder is this. If I hide this, that's your autoencoder. So your autoencoder optimizes reconstruction on the training data. However, it does not have the regularization such that whatever is being learned by the neural network, by like encoder, does not overfit only on the training points. This regularization term basically tells the neural network if this is my, let's say, 5 training points, do not try to put like very high picks of probability of likelihood only on these 5 points, because this is what our model would normally do. Like if you let it loose, if you don't inform the model, for the model, it makes more sense to put all the probability mass on these 5 points. However, that's not logical, right? Like we expect that, there are stuff here also. So what we do with the entropy, we say that our approximate posterior, so what we expect our codes to be, is like also in between. So there should be more like stuff here. Now, how does this stuff look like? So that's our prior. If it is a Gaussian, if we assume that our prior is a Gaussian, we ask the yellow stuff that the network fills in should be as close as possible to a Gaussian in the end. If we expect the yellow stuff, or if we expect our latents to be having like a different shape, a different distribution, then we will have to inform our neural network so that it redistributes. If we, for instance, say that, well, our data points lie on the circle, for instance, if I take a picture of a car, like of the chair, take pictures all around, geometrically expect that the change that I see in my input will be proportional to the rotation of the perspective. So it's not unreasonable to think that my latent space will look like a ring, and each coordinate, each like location in the ring, will correspond to a different angle. And in that case, for instance, having a Gaussian latent space, so a Gaussian prior, is not very meaningful because likely there's not much here. So in that case, we should not pick a Gaussian for our latent, for our prior distribution. Clear? So we have the inference model. It's called approximate posterior because it approximates the posterior distribution, the variational distribution. The true posterior, the P of z given x. You can also see it as inference or decoder. The generative model decodes, so it's a neural network. And what does decode mean? That if I have as input a noise variable or whatever, like a sample from my distribution, from my latent distribution, then I should generate something meaningful. If I have Gaussian latent space, these are my latent codes is one parameter for my mu, one for my sigma, and then the noise variables comes externally. The output is probabilistic, can be probabilistic, so depending on our types of data, we have to pick something. If we have continuous values, Gaussian output makes sense. We just then need to adapt our P of x given c, say that this looks like a Gaussian, and then took the logarithm of the Gaussian to compute the final likelihood. And when we want to generate novel images, we simply need to sample, we ignore this. When we want to sample new images, generate new images, we ignore the encoder, right? Like there is no encoder. We sample a new sample, and then we pass it through our decoder and hopefully generate something meaningful. And hopefully it's going to be like this. Meaningful will be, well, of course it will be most probably a coordinate that has not been seen before. And the hope is that this new coordinate will still create an image that looks plausible. For the prior distribution, we have to pick a prior distribution that resembles the manifold we expect in our data. So this is what I was saying. If I have a ring manifold, I should have a ring latent distribution. If we have sparse latents, if we want to encourage sparsity, we should not use Gaussian because Gaussian is not sparse. You can see the prior distribution as a regularizer, as I said here. You want to force the model to put likelihood everywhere. This KL term can be analytically derived. For instance, when you've got the Gaussian prior distribution, and then you've got also a Gaussian approximate posterior. And if it's not possible to analytically derive, you can actually compute it or try to estimate it with Monte Carlo, if that is possible, if you've got the necessary conditions for that. Because after all, this is an integral, and you have here a density function. Okay, typo, I'll fix that. Now, if you use Monte Carlo estimation, if you can compute analytically, it's best. Because that's it, like you compute, it's an equation, right? Like it's just, you compute it. Monte Carlo estimation is a practical, like empirical approximation. It solves your problem. However, it increases the computational cost, potentially, if you have more than one samples. And also increases potentially the variance. This is what I meant here about interpolation. So interpolation means like picking coordinates that are in between what we've seen during training. And variational autoencoders seem to be very good at that. They force the model to give good, make good generations even on latent locations, latent coordinates that have not been seen before. And you can also see it from the perspective of clustering. So it clusters things together in regions of the latent space that are somehow coherent. So for instance, you can go from 0s to 6, to 2s and 5s and 4s. So this is basically, so it's a 2D latent space, and for whatever coordinate, to make it easy, they generated the image that corresponds to this, to the coordinate of the latent space. And so you see that you smoothly go to different, like you generate smoothly different digits. A bit more on ELBO. Yeah, so we discussed a bit quickly, but I thought maybe I can give a very quick recap, because I think the previous time it felt a bit alien, not very motivated. So we derived the ELBO in the first place as a way of solving the integral that appears in the joint likelihood. Again, generative models means that you will have somewhere an integral. You cannot avoid it. What you can do is try to make it easier to compute it. So make things tractable. Here the integral is because we have to integrate out the latent variable, and we have to integrate it out because we simply don't know what is this variable. We have to take into account all possible values for z. But you don't have to start from here, right? You can have like a different starting point for at least latent variable models. So perhaps we can say that we're interested mostly on the encoding part. Let's say we want to derive optimal latent codes or inputs. So if my input is x, what is the best possible representation for my input? Now this is then takes also the form of like some form of likelihood. In this case, it's the true posterior. It's what we call the true posterior. The true posterior tells me, given my input, what are the likelihoods for all like the different values of my latent variable. So basically, this should pick very highly for values of z that are very good representations by my input. Now, if I do the base rule, okay, another typo here. then I can rewrite this as p of x comma z over the integral of p of x comma z with respect to z. Again, an integral, we cannot avoid it. So this actually now brings our intractability. And what is, oh, too many times. Let me fix that. Let's fix this one as well then. So we want to find, this is a true posterior, like let's say we are fundamentally interested not in how to compute the joint likelihood, like that's one way of looking at it. We don't care about that per se. Let's say we care about how do I find my optimal latent representation, and I say my latent representation is itself a distribution. So how do I recover, how do I approximate this distribution? Well, a reasonable way to do this is have another distribution, Q of z, my important sampling distribution, and try to approximate this best as possible, which means that I would like, I need then a measure of difference. So a measure of finding what's the difference between the distributions. KL divergence is a good one. So KL is the integral of Q, the first term, times the logarithm of Q over Z, over P. Then I rewrite P of Z given X based on my base rule here. And then with some standard rearrangements, I end up, like, this is the important bit. The KL, the distance between my approximate distribution, my variational distribution, and my true posterior is the expectation of the logarithm of the joint likelihood over the importance sampling when computing expectation with respect to the importance sampling times the logarithm of my evidence. And now what do I know? That this is always positive. The KL divergence is always positive. So this will be always positive. So my logarithm of P of X goes on the other side, and it's always higher than this. And now this is the ELBO. So that's the second way of deriving the ELBO. The second way of deriving the ELBO is by making sure that we want to meet that by minimizing the KL divergence between the variational distribution Q of Z and my true distribution. If I, instead of QZ, my variational distribution, I've got amortized variational inference, then I simply replace Z with Z given X. Nothing changes. Like this changes, and like that's it. So again, we discussed this a bit the previous time, but very quickly again. Hopefully now it's a bit clear, like the motivation is a bit clear. By optimizing for a higher ELBO, this is my evidence. This is my true, like the quantity that I truly care about. I cannot estimate it, however, easily, let alone optimize for it. What I can optimize for is the ELBO. This is what we just saw. What's the relation between the evidence, the ELBO, and the KL between the variational distribution and the true posterior. This will always be positive, but I can minimize it. I can pick a location where it's small as possible. And this is literally what I'm doing here with my optimization. I'm trying to find where my model minimizes the gap. Higher ELBO means the gap becomes smaller. So if I push this is, sort of stuck constant for my data. When I maximize this, then this becomes smaller, right? Like this goes high, this has to go low so that this remains the same. And higher ELBO means also that our latent vectors become better because this becomes smaller, right? Like if my approximate, my variational approximation is close to the true posterior, this means that my approximation is really good. So I've got really, really good calls. One of the reasons why, well, there are several reasons that we know or that we hypothesize. One of the reasons why VAEs, the standard VAEs at least, cannot do as well as other more modern generative models is that there's always a gap. So stable diffusion models, normalizing flows, autoregressive models can directly optimize for the true objective, whereas VAEs will always have a gap. Of course, that's one of the reasons. Like another reason is that VAEs make an assumption of Gaussianity. That's not always the case, and so forth. Variational inference graphically, you start from a random location. This is your true posterior. Through optimization, you want to go to the location in your family of, all possible parameters of your approximate distribution. So you want to pick the one that is as close as possible to your true posterior, like that's literally what you're doing. If this would be inside, perfect. We actually have the possibility to find the true posterior exactly. Yeah, okay, and we saw that, like, okay, we discussed it before, so in the interest of time, let's skip. And in the introductory lecture for generative models, we discussed about the battle between tractability and flexibility. How would you comment about this trade-off with respect to variational autoencoders? Are they tractable? Are they flexible? What are the problems? So they are more tractable, right? Why?
Use tricks to make them more tractable.
Right. We add latent variables, and by that we make them more tractable. So we make them tractable by adding auxiliary variables that normally we know nothing about, and thus we have to make assumptions. Our models, for whatever you do in AI, or even outside AI, in science in general, your models will always be as good as your assumptions. If your assumptions are not good anymore, they're not a faithful representation of reality, then your models are not going to be good anymore. VAEs are very good for as long as the assumptions make sense. For instance, you got the Gaussian latent space or whatever other latent space you pick for your auxiliary variables. Mean field, amortized, KL divergence, like all these are assumptions, or they are different ways of looking at the same assumption. For as long as this assumption is good enough, then your model will be good enough. This comes at the cost of decreased flexibility. If you assume that your latent space is Gaussian, when your latent space is not Gaussian, then you're actually losing something. Your assumption is not good enough anymore. Okay, wrapping up, we discussed what are latent variable models, variational inference, amortized variational inference, variational autoencoders, their parameterization trick and variance reduction, and some insights. latent variable models are generally a very important class of algorithms. I understand that like not everything is easy to digest, but you know, when you try to think about it, think of it like step by step. How would you code it? How would you literally code it? Whenever there is a step in this thought process for which you have, hey, wait a minute, like that's not super obvious. I mean, I can make a hack. Whenever you feel that you could do a hack, then that's probably something that you can work on, that you can fix. That this is actually the reason why VAEs are challenging, or whatever other model is challenging. And it's like, you know, a way of figuring out what are, you know, gaps in knowledge. And when you have these gaps, please come find me so we can discuss further. Okay? Thanks.
Nothing.